This is the apparatus for the measurement of the dryness fraction. The steam comes from the boiler as saturated steam in this pipe, and at this branch pipe it comes down to this valve. We open the valve and this will supply saturated steam into the apparatus for measurement the dryness fraction. So we measure a P1, which is the supply pressure into the apparatus, and also we measure T1 through this switch. So you can see this switch steam supply, it means to the left side T1 steam supply, and to the left is if we push the switch to the left, it will be throttling chamber temperature T2. So the steam, saturated steam, enters the separating calorimeter. This is first calorimeter, separating calorimeter. In this calorimeter, the steam changes direction in the flow, and the water will be separated from the dry steam and accumulate at the bottom of the separating calorimeter. And you can see this will actually, glass tube will show the level of the water separated, and we can read the value of the separated water in cc, and the symbol we use MWS. MWS, it means mass of water separated in the separating calorimeter. Then the steam leaving is assuming it is dry steam according to the separating calorimeter. This steam leaving from it, it will be MVS, mass of dry steam leaving the separating calorimeter. But we'll find out that actually the steam is not really dry steam in here. It is still saturated steam. So that's why we need the throttling calorimeter to make more accurate measurement for the dryness fraction. So in the throttling calorimeter, the saturated steam, which is actually which we assumed it is dry steam, it is expanding in here in the into the cylinder in the throttling calorimeter. By expansion, the steam becomes superheated, and the enthalpy H1 before the throttling calorimeter equal to H2 in the throttling calorimeter. We can find a relation, actually dryness fraction XT, based on the enthalpy properties before and in the throttling calorimeter. So we can find this equation, which is equation 2, for finding XT. And the steam leaving the, of course, in the throttling calorimeter, we measure T2, as I said there, using the switch to the left, to the right side, in degrees centigrade. And also we measure the pressure P2 in the throttling calorimeter, which is in millimeter mercury in the manometer. Then the superheated steam is condensated in this condenser. It leaves and it will pass to the condenser, then it is collected there through this pipe into a measuring beaker, which we can actually measure how much volume of water in cubic centimeter cc to measure the mass of dry steam which is leaving the separating calorimeter. So we condensate it and we can find how much is MV, mass of MVS, which is the mass of dry steam leaving the separating calorimeter. So taking this measurement, I repeat again, so the readings, we need P1 and T1 at the supply, and we need P2 in the throttling calorimeter and T2 in the throttling calorimeter. We need MWS, the separated water in the separating calorimeter, and we need MVS, which is the mass of dry steam leaving the separating calorimeter. Then we can use equation 1, 2, and 3 to find the dryness fraction. For the steam flow measurement, of course, we have the saturated steam supply. It will pass to the orifice in here. So inside here there's orifice, and across the orifice we have the pressure drop. We measure the pressure drop delta P using this manometer in millimeter mercury, and using the equation for the orifice, which is mass flow rate equal constant square root of density times delta P, which is across the orifice. This will give us actually the mass flow rate of steam through an orifice. Then we can calculate the mass flow rate of steam. So this is for dry steam, of course, if we use the density. We can use it for saturated steam. We divided the density by dryness fraction over x. Then we can get it, the mass flow rate for saturated steam.